Tonight, we're going to visit somewhere that will chill you to your very soul. Not the Arctic. Not Antarctica. Not even the dark side of Pluto. We're going somewhere so unimaginably cold that the temperature hovers just barely above the point where all motion stops. Where atoms themselves slow to an almost frozen crawl. We're going to the Boötes Void, a region of space so empty, so vast, and so impossibly cold that it challenges everything we think we understand about the universe. This place is 330 million light years across. Inside it, there's almost nothing. No stars to warm the emptiness, no galaxies to break the silence, just cold. Pure, absolute, terrifying cold. And by the end of this journey, you'll understand what cold truly means. Before we dive into this exploration, if you find these kinds of deep journeys through the cosmos interesting and thought-provoking, a quick like or subscribe would really help the channel grow. It's a small thing for you, but it makes a huge difference for me. Get yourself warm and comfortable, settle in, as we explore the coldest place ever to exist. Let's begin. Let's start with something you think you understand. Cold. You know what cold feels like? You've walked outside on a winter morning and felt the bite of frigid air against your skin. You've opened a freezer and felt that wave of chill wash over you. You've held an ice cube and felt it sting your fingers. You've shivered under blankets on a night when the heating failed. You know cold. Or at least you think you do. But here's the thing. The coldest day you've ever experienced, the most bone-chilling winter night you can remember, is actually incredibly warm by cosmic standards. Not just warm, blazing hot. The coldest temperature ever recorded on Earth, about -89 degrees Celsius, at Antarctica's Vostok Station back in 1983, would be considered scorching in the places we're going to explore tonight. If you took that Antarctic air and transported it to certain regions of the universe, it would radiate heat like a furnace. It would glow with thermal energy. It would be hundreds of degrees warmer than its surroundings. Because out there, in the vast emptiness between galaxies, in the enormous voids that make up most of the universe's volume, cold takes on a meaning that's almost impossible for human minds to grasp. We're going to journey tonight to places so cold that the very concept of temperature begins to break down. Places where atoms barely move. Places where the laws of physics operate differently than anything you've ever experienced. Places that are just a few degrees above the point where all motion stops entirely. To understand where we're going, we first need to understand what temperature actually is. Because temperature isn't just a number on a thermometer. It's not just a feeling of discomfort when you forget your jacket. It's something far more fundamental. Something built into the second. A block of ice has molecules vibrating more slowly, locked in a crystal structure but still oscillating back and forth. Even solid steel, even diamond, even the coldest ice you've ever touched has atoms that are vibrating with thermal energy. And at the very bottom of the temperature scale, at a point called absolute zero, particles would theoretically stop moving entirely. They would have zero thermal energy, zero motion, complete stillness. This is the coldest possible temperature, the end of the line, the floor beneath which nothing can exist. Absolute zero sits at -273.15 degrees Celsius. Scientists prefer to use a different scale called the Kelvin scale, where absolute zero is simply 0 Kelvin. On this scale, water freezes at 273 Kelvin and boils at 373 Kelvin. The Kelvin scale is useful because it starts at the true bottom. 0 means 0. zero motion, zero thermal energy, zero everything. Nothing can be colder than absolute zero. This isn't a limitation of our technology or our understanding. It's a fundamental law built into the structure of the universe. You can't have less than zero motion. You can't move less than not moving at all. It would be like asking for a length shorter than 0 inches, or a time before the beginning of time. The concept simply doesn't make sense within the framework of physics as we understand it. Here's something remarkable though. No matter how hard you try, no matter what technology you develop, you can never actually reach absolute zero. You can get incredibly close, tantalizingly close. Scientists in laboratories have achieved temperatures of billionths of a Kelvin, so close to absolute zero that the difference is almost meaningless. But you can never quite get there. It's like trying to reach the speed of light. You can approach it, get arbitrarily close, pour infinite energy into the attempt, but crossing that final barrier is impossible. There's always a little bit of motion left, always a tiny amount of energy that refuses to be removed. This impossibility is enshrined in the third law of thermodynamics, one of the most fundamental principles in physics. It states that no finite process can reduce a system to absolute zero. You can get close, but you can't arrive. The coldest places in the universe, as we'll discover, hover just above this limit. They approach stillness, but never quite achieve it. On Earth, we deal with a relatively narrow range of temperatures. The coldest natural temperature ever recorded was that minus 89 degrees Celsius in Antarctica. The hottest natural temperature was about 56 degrees Celsius in Death Valley, California, recorded in 1913. That's a range of roughly 145 degrees. It seems like a lot when you're experiencing it. The difference between a scorching summer day where the asphalt burns through your shoes and a brutal winter night where exposed skin freezes in minutes feels enormous. These temperature extremes have shaped human civilization, determined where we can live, influenced our architecture, our clothing, our entire way of life. But in cosmic terms, this range is laughably small. The universe operates on a temperature scale that spans from just above absolute zero to trillions upon trillions of degrees. The difference between the coldest Antarctic night and the hottest desert day is like the difference between two rooms in your house. Barely noticeable, practically identical. The cosmos doesn't care about temperature ranges that concern humans. The cosmos deals in extremes we can barely imagine. The hottest places in the universe make our hottest summers look like absolute zero in comparison. The cores of massive stars reach temperatures of about 15 million degrees Celsius. That's hot enough to fuse hydrogen atoms into helium, releasing the energy that makes stars shine. But even that is modest compared to what's possible. When massive stars explode as supernovae, the temperatures in the collapsing core can exceed 100 billion degrees. At these temperatures, matter behaves in ways that seem almost impossible. Atoms are completely torn apart. Protons and neutrons break down into their constituent quarks. The fundamental forces of nature behave differently than they do under normal conditions. The jets of matter shooting out from supermassive black holes can reach temperatures of trillions of degrees. In particle accelerators here on Earth, scientists have created temperatures of several trillion degrees for tiny fractions of a second, recreating conditions that existed just microseconds after the Big Bang. At these temperatures, ordinary matter simply cannot exist. Everything becomes a soup of fundamental particles, quarks and gluons swimming in a plasma hotter than anything natural in the present-day universe. And at the other extreme, in the coldest places in the universe, something equally strange happens. Matter approaches a state of perfect stillness. Quantum effects become dominant. The normal rules of physics give way to something more subtle, more mysterious, more beautiful. But we're getting ahead of ourselves. Before we can understand the coldest places, we need to understand the baseline temperature of the universe. Because space isn't really empty. And it isn't really at absolute zero. There's something out there. Something permeating every cubic centimeter of the cosmos. Something that sets a floor on how cold things can naturally get. About 13.8 billion years ago, the universe began in an event we call the Big Bang. In the first moments of existence, everything was unimaginably hot. We're not talking about temperatures you can visualize or relate to. We're talking about temperatures so extreme that the laws of physics as we know them hadn't yet fully emerged. In those first fractions of a second, temperatures exceeded 10 trillion degrees. The entire observable universe, everything that would eventually become every galaxy, every star, every planet, every atom in your body, was compressed into a space smaller than an atom, blazing with impossible heat. The universe at that moment was a seething cauldron of energy. Light couldn't travel through it because the medium was so dense, so hot, so energetic the photons were constantly absorbed and re-emitted. The universe was opaque, like being inside an explosion, surrounded by blinding white light in every direction. Matter as we know it couldn't exist. Atoms couldn't form because any atom that tried to come together would immediately be blasted apart by the intense radiation. Then the universe began to expand. And as it expanded, it cooled. This is a fundamental property of gases and radiation. When you expand something, it cools down. When you compress something, it heats up. You've experienced this if you've ever used a bicycle pump. The pump gets warm as you compress the air inside. The air molecules are squeezed into a smaller space, they collide more frequently, and the temperature rises. The reverse happens when air expands. The molecules spread out, collide less frequently, and the temperature drops. This is why the air coming out of a spray can feel cold. It's expanding rapidly as it leaves the pressurized container. The universe has been expanding for 13.8 billion years. And during all that time, it's been cooling. At first, it cooled rapidly. Within the first few minutes, the temperature dropped from trillions of degrees to about 1 billion degrees. Nuclear fusion occurred during this period, creating the first atomic nuclei, primarily hydrogen and helium. By about 380,000 years after the Big Bang, the universe had cooled to about 3,000 degrees, cool enough for electrons to combine with nuclei and form neutral atoms. At this moment, the universe became transparent. Light could finally travel freely through space. The radiation that was released at that moment, the first light that could stream unimpeded through the cosmos, is still with us today. We call it the cosmic microwave background, or CMB, and it's one of the most important discoveries in the history of cosmology. The cosmic microwave background was first detected in 1964 by Arno Penzias and Robert Wilson, two radio astronomers working at Bell Labs in New Jersey. They were trying to calibrate a highly sensitive radio antenna for satellite communications, but they kept picking up a mysterious noise. No matter which direction they pointed the antenna, they detected a faint microwave signal. They checked everything. They cleaned pigeon droppings off the antenna. They eliminated every possible source of interference, but the signal persisted. It was coming from everywhere, from every direction in the sky, from space itself. What Penzias and Wilson had discovered, though they didn't immediately realize it, was the afterglow of the Big Bang. The radiation that had been released when the universe first became transparent, 380,000 years after creation, had been traveling through space ever since. Over billions of years, as the universe expanded, that radiation had stretched. Its wavelength had increased. What was once visible light, blazing at 3,000 degrees, had cooled and stretched into microwaves. The light of creation had become invisible to human eyes, but detectable by radio telescopes. Today, the cosmic microwave background has a temperature of about 2.725 Kelvin. That's roughly minus 270 degrees Celsius, or minus 454 degrees Fahrenheit. It's cold, unbelievably cold by human standards. The warmest winter coat, the thickest insulation, would do nothing against cold like this. At 2.7 Kelvin, air would be frozen solid. Steel would become brittle enough to shatter. Even helium, the element that remains liquid at the lowest temperatures of any substance, would solidify at this temperature under sufficient pressure. But it's not zero. It's not absolute zero. There's still energy there. Still motion. Still warmth, even if that warmth is almost imperceptible. The universe isn't dead. It's not frozen solid. It still hums with the residual energy of creation, a faint echo of the Big Bang that pervades every corner of the cosmos. This cosmic microwave background sets a floor for the temperature of the universe. In theory, nothing can naturally be colder than the CMB because the CMB is everywhere. It's radiation that fills all of space uniformly. There's no escaping it. No matter where you go in the universe, no matter how far you travel from any star or galaxy, you'll still be bathed in this faint glow of ancient light. It's like a background hum that you can't turn off. A cosmic temperature minimum that applies everywhere. Any object in the universe will absorb this radiation and warm up to at least the CMB temperature, unless something unusual is happening. If you placed a perfectly insulated block of matter in deep space, far from any star, it would gradually cool by radiating its heat away. But it would never cool below 2.7 Kelvin. At that point, it would be in thermal equilibrium with the cosmic background. It would absorb energy from the CMB at exactly the same rate it radiated energy away. The CMB acts like the universe's thermostat, keeping everything at a minimum temperature of about 2.7 Kelvin. Think about what this means. No matter where you go in the observable universe, no matter how remote the location, no matter how empty the space, you'll never find anything naturally colder than this temperature. The cosmic microwave background is a universal constant, a property of space itself. It's the coldest natural bath the universe provides. But here's where things get interesting. Not all parts of the universe have the same density. Not all regions have the same amount of matter. The universe isn't uniform like a perfect gas in a container. It has structure. It has clumps and voids. It has regions of density and regions of emptiness. When astronomers map the distribution of galaxies across the cosmos, they find a remarkable pattern. Galaxies aren't spread evenly like dots on a uniform grid. Instead, they cluster together along filaments and walls, forming an enormous structure that cosmologists call the cosmic web. Imagine a three-dimensional spider's web, with strands of galaxies connecting denser nodes where galaxy clusters form. This web stretches across the entire observable universe, a scaffolding of matter built by gravity over billions of years. In the dense regions of this web, where galaxies cluster together, there are lots of stars. Stars produce light and heat. They warm their surroundings. The temperature in a galaxy or near a star is much higher than the CMB baseline. Our sun's surface is about 5,800 Kelvin. Even the dark space between stars in our galaxy is warmed by starlight to temperatures of a few tens of Kelvin, well above the cosmic background. But between the filaments, between the strands of the cosmic web, there are vast regions of almost nothing. These regions are called voids, and they're where we find the coldest natural places in the universe. In a void, there's nothing to produce heat. No stars burning with nuclear fire. Almost no galaxies glowing with the combined light of billions of suns. Almost no matter at all. Just empty space, stretching for millions upon millions of light years, with only the faint glow of the cosmic microwave background to provide any warmth whatsoever. In these voids, the temperature approaches the CMB baseline of 2.7 Kelvin. It gets as cold as the universe naturally allows, minus 270 degrees Celsius, just a few degrees above absolute zero, just a few degrees above perfect stillness, just a few degrees above the point where motion itself would cease. Let me put this in perspective with a comparison. Water freezes at 0 degrees Celsius, which is 273 Kelvin. The coldest day ever recorded on Earth at Antarctica's Vostok station was about 184 Kelvin. Liquid nitrogen, the stuff they use to flash freeze things in laboratories and make fog for special effects, boils at 77 Kelvin. Liquid helium, the coldest common cryogenic fluid, boils at just 4 Kelvin. And the cosmic microwave background, the temperature of the voids, is at 2.7 Kelvin. The voids of the universe are colder than liquid helium, colder than any natural environment on any planet or moon in our solar system, colder than anything humanity experienced until we developed the technology to create extreme cold artificially in laboratories. The voids represent a natural state of cold that's almost at the theoretical limit, almost at the point where motion stops entirely. But what does it mean to be that cold? What would it feel like? Would you even feel anything at all? The truth is, at temperatures this low, the question of feeling becomes meaningless. Your nerve cells operate through chemical reactions, and chemical reactions require a certain minimum temperature to proceed. At 2.7 Kelvin, no chemical reaction would occur in your body. Your neurons wouldn't fire. Your synapses wouldn't transmit signals. You wouldn't feel cold because you wouldn't feel anything. You would simply stop functioning, frozen in an instant. Your biological processes halted before you even registered what was happening. But the physics of extreme cold goes far beyond what it would do to a human body. At temperatures approaching absolute zero, matter itself behaves differently. Quantum effects become dominant. The normal rules of physics give way to something stranger and more beautiful. At everyday temperatures, atoms behave more or less like tiny billiard balls. They bounce around, collide, transfer energy. Classical physics describes their behavior quite well. But as you cool matter down, as you remove thermal energy and approach stillness, quantum mechanics takes over. Particles stop behaving like discrete objects with definite positions and velocities. They become waves of probability, spread out over space, existing in multiple states simultaneously. At extremely low temperatures, some materials become superconductors, able to conduct electricity with zero resistance. Others become superfluids, able to flow without friction, climbing up the walls of containers, passing through microscopic holes. Atoms can form collective states called Bose-Einstein condensates, where millions of particles act as a single quantum entity, occupying the same quantum state, behaving as one. These phenomena only occur at temperatures within a few degrees of absolute zero. They're the signature of the quantum realm, the regime where the deepest laws of physics become directly observable, and they hint at what conditions might be like in the coldest natural places in the cosmos. The voids of the universe are laboratories for extreme physics. They're places where matter, if any exists there, experiences temperatures close to the quantum limit. They're windows into the fundamental nature of reality, places where the everyday rules break down and something more profound emerges. And the largest, most famous, most studied of these cosmic voids is a structure so vast and so empty that when astronomers first discovered it, they couldn't believe what they were seeing. A place called the Boötes Void. A place sometimes called the Great Nothing. A sphere of emptiness 330 million light years across, containing almost nothing but cold and darkness. Let me tell you about a place where almost nothing exists. A place so empty that when astronomers first discovered it, they assumed their instruments had malfunctioned. A place so vast that it challenges our ability to comprehend emptiness itself. The Boötes Void sits approximately 700 million light years from Earth, in the direction of the constellation Boötes the Herdsman. When you look up at the northern sky on a summer evening and spot Boötes with its bright orange star Arcturus, you're looking toward one of the most profound absences in the entire observable universe. Behind those familiar stars, far beyond the boundaries of our Milky Way galaxy, lies a sphere of emptiness so enormous that light itself needs 330 million years to cross it. 330 million years. When light began its journey across the Boötes Void, dinosaurs hadn't evolved yet. The Atlantic Ocean didn't exist. The supercontinent Pangaea hadn't even finished forming. That's how long it takes for the fastest thing in the universe to traverse this cosmic desert. And during that entire journey, that light would encounter almost nothing. Just darkness, just cold, just the faint whisper of the cosmic microwave background. The discovery of the Boötes Void reads like a detective story. In 1981, astronomer Robert Kirshner and his colleagues at the University of Michigan were conducting what should have been a routine survey. They were mapping the distribution of galaxies in a section of the northern sky, using redshift measurements to determine how far away each galaxy was. Redshift is the stretching of light from objects moving away from us. The more the universe has expanded between us and a distant galaxy, the more its light is shifted toward the red end of the spectrum. By measuring these redshifts, astronomers can construct three-dimensional maps of the cosmos, showing not just where galaxies appear in the sky, but how far away they actually are. What Kirshner's team found in the direction of Boötes was startling. There was a gap, a huge spherical region where galaxies simply weren't present. They had expected to find a relatively uniform distribution of galaxies, perhaps with some clustering here and there, but basically galaxies scattered throughout the volume they were surveying. Instead, they found a hole, a vast empty bubble in the cosmic fabric. The initial reaction from the astronomical community was skepticism. Surely Kirshner's team had made a mistake. Surely there were galaxies in that region that they simply hadn't detected. Perhaps their survey was incomplete. Perhaps fainter galaxies lurked in the void, too dim to see with the telescopes of the time. Better instruments would reveal the missing matter. More careful observations would fill in the gap. The void couldn't possibly be as empty as it appeared. But subsequent observations only confirmed the initial findings. The Boötes Void is real. It's genuinely almost empty. And its existence tells us something profound about the nature of the universe we inhabit. To understand just how remarkably empty the Boötes Void is, we need to compare it to our local cosmic neighborhood. Because from our perspective here on Earth, space might seem full of stuff. Stars everywhere, galaxies visible through telescopes, a universe teeming with matter. But our perspective is skewed. We live in a relatively dense region of the cosmos. The Milky Way isn't just any galaxy. It's a large spiral galaxy containing hundreds of billions of stars. And we're not isolated. We're part of a community. The Milky Way belongs to a small collection of galaxies called the Local Group. This gravitationally bound family contains somewhere between 50 and 80 galaxies, depending on how you count the smallest dwarf galaxies. The two largest members are the Milky Way and Andromeda, both massive spiral galaxies. The rest are smaller, some containing only a few billion stars, some containing mere millions. The Local Group spans a region about 10 million light-years across, with galaxies scattered throughout, orbiting their common center of gravity, interacting gravitationally, occasionally colliding and merging. Beyond the Local Group, we're part of a larger structure called the Virgo supercluster. This is a collection of galaxy groups and clusters spanning about 110 million light-years. It contains roughly 100 galaxy groups and clusters, including the massive Virgo cluster at its heart. The Virgo cluster alone contains over 1,000 galaxies, including giants like M87 with its supermassive black hole that scientists famously photographed in 2019. And even the Virgo supercluster is just a small part of something larger. In 2014, astronomers discovered that our supercluster is actually a lobe of an even more enormous structure called Laniakea, Hawaiian for immeasurable heaven. Laniakea contains about 100,000 galaxies, spread across 520 million light-years. All of these galaxies, including our Milky Way, are slowly flowing toward a gravitational focal point called the Great Attractor. The point of all this is simple. Wherever you look in the universe, you typically find galaxies. Not uniformly distributed like dots on a perfectly regular grid, but clustered along filaments and walls, forming an intricate cosmic web of matter. Some regions are denser, packed with galaxy clusters. Some regions are less dense, containing only scattered dwarf galaxies. But galaxies are everywhere. They're the basic units of cosmic structure, and they permeate the observable universe. The average density of the universe tells us roughly how many galaxies we should expect to find in any given volume of space. Based on this average, a region the size of the Boötes Void should contain roughly 2,000 galaxies, 2,000 island universes, each containing billions upon billions of stars. 2,000 points of light scattered through that 330 million light-year sphere. 2,000 chances for planets, for chemistry, for complexity, perhaps even for life. Instead, astronomers have found approximately 60 galaxies inside the Boötes Void. 60 instead of 2,000. That's about 3% of what we'd expect. 97% of the galaxies that should be there are missing. The void isn't perfectly empty, but it's astonishingly close. It's as if you expected to find a city of 2,000 people and discovered only 60 inhabitants huddled in scattered camps throughout an otherwise deserted landscape. And even those 60 galaxies aren't distributed randomly throughout the void. They tend to cluster together in small groups, often near the void's edges, as if seeking safety in numbers, huddling together for warmth in the cosmic cold. Some astronomers have suggested that these galaxies might form a filamentary structure, threading through the void, a thin strand of matter in an otherwise empty volume. Others have proposed that the galaxies are slowly migrating toward the void's edges, drawn by the gravity of the denser regions outside. This clustering behavior makes the void's interior even more empty than the raw numbers suggest. If you positioned yourself at the true center of the Boötes Void, the nearest substantial galaxy might be 50 million light-years away or more. In every direction you looked, you would see virtually nothing. Just darkness stretching away toward an impossibly distant rim. Let me try to help you visualize what this would be like. Right now, on Earth, when you look up at the night sky on a clear, dark night away from city lights, you see thousands of stars with your naked eye. About 6,000 stars are visible under perfect conditions, scattered across the celestial sphere. With binoculars, you can see tens of thousands more. With a small telescope, millions. And among those stars, you can spot other galaxies. The Andromeda Galaxy appears as a fuzzy smudge. The Magellanic Clouds glow in the southern sky. The universe appears full of light and structure and possibility. Now, imagine being transported to the center of the Boötes Void. Not to a planet orbiting a star, because there are almost no stars nearby. Just floating in space, protected somehow from the vacuum, looking out at your surroundings. What would you see? Almost nothing. The nearest galaxy, some 50 million light-years distant, would be far too faint to see with the naked eye. Even with the powerful telescope, you'd have to search carefully to find anything at all. The stars you're accustomed to seeing, the familiar constellations, the comforting band of the Milky Way stretching across the heavens, all of it would be gone. You would be surrounded by darkness so complete that it would make the darkest nights on Earth seem bright by comparison. Just blackness. Just emptiness. Just the cold glow of the cosmic microwave background. Invisible to human eyes, but present nonetheless, bathing you in ancient radiation from the dawn of time. This profound emptiness isn't just a visual experience. It has real, measurable physical consequences. In a region with no galaxies, there are no stars. Stars are the universe's furnaces, fusing hydrogen into helium and releasing tremendous amounts of energy in the process. They warm the space around them. They provide light that carries energy across millions of light years. In our galaxy, even the space between stars is warmed by starlight to temperatures of a few tens of Kelvin, well above the cosmic microwave background. But in the Boötes Void, there's almost no starlight. The handful of galaxies that exist there are so scattered, so remote from each other, that their collective output of light and heat is negligible. The only significant energy source in the deep void is the cosmic microwave background itself, that faint afterglow of the Big Bang that permeates all of space at a temperature of 2.7 Kelvin. And that means the temperature in the Boötes Void approaches this cosmic minimum. 2.7 Kelvin, minus 270 degrees Celsius, just a few degrees above absolute zero, just a few degrees above the point where all thermal motion would cease. Let's think about what this temperature actually means in practical, physical terms. At 2.7 Kelvin, everything is frozen. Not just water, which freezes at 273 Kelvin. Not just carbon dioxide, which freezes at around 195 Kelvin. Not just nitrogen or oxygen or argon. Everything. Every common substance, every metal, every mineral, every compound you can name would be frozen solid at this temperature. The only exception is helium. That quirky element that refuses to solidify even at absolute zero under normal pressure. Helium remains liquid at the coldest temperatures achievable, a quantum mechanical consequence of its extremely low mass and weak interatomic forces. But even helium would be nearly motionless at 2.7 Kelvin, its atoms drifting with only the faintest thermal energy. Any spacecraft that ventured into the deep Boötes Void would face engineering challenges unlike anything encountered in our solar system. Without active heating systems consuming enormous amounts of energy, the spacecraft would quickly cool to the ambient temperature. Electronics would fail as their components became superconductors or ceased functioning altogether. Lubricants would freeze solid, locking moving parts in place. Metals would become brittle, prone to fracturing at the slightest stress. Seals would fail as materials contracted unevenly in the cold. The spacecraft would become a frozen tomb drifting through emptiness. But the physical challenges go beyond mere engineering difficulties. At temperatures near 2.7 Kelvin, we're approaching the regime where quantum mechanics becomes dominant over classical physics. At normal temperatures, the quantum behavior of particles is masked by their thermal motion. Everything is jiggling and bouncing around with such energy that the subtle quantum effects are washed out, averaged away, invisible. Particles behave more or less like tiny billiard balls, obeying intuitive rules of motion and collision. But as you cool matter down, as you remove thermal energy and approach stillness, quantum effects emerge from hiding. Particles stop behaving like tiny billiard balls and start behaving like waves. They become delocalized, spread out in space, existing as probability distributions rather than definite points. They become uncertain, occupying multiple states simultaneously until observed. The clean, predictable world of classical physics gives way to the strange, probabilistic world of quantum mechanics. How did the Boötes Void form in the first place? Why is this particular region of space so extraordinarily empty when other regions are filled with galaxies? The answer lies in the very early universe, in conditions that existed shortly after the Big Bang, in fluctuations so small that they seem almost insignificant yet prove to be the seeds of all cosmic structure. In the first moments after the Big Bang, the universe was almost perfectly uniform. Matter was spread nearly evenly throughout all of space, a hot, dense soup of particles and radiation with no galaxies, no stars, no structure of any kind. But this uniformity wasn't quite perfect. There were tiny fluctuations, microscopic variations in density from place to place. These fluctuations were incredibly small, differences of maybe 1 part in 100,000. In any given region, the density might be 0.001% higher or lower than average. Barely anything. Almost nothing. But almost nothing isn't quite nothing. And gravity, patient and relentless, amplifies small differences over cosmic time. Over billions of years, those tiny density fluctuations grew. Regions that were slightly denser than average attracted more matter through gravity. As more matter accumulated, the gravitational pull grew stronger, attracting still more matter. A cosmic snowball effect. These overdense regions collapsed and fragmented, eventually forming the first galaxies. Galaxies merged with other galaxies, forming clusters. Clusters connected through filaments, forming the cosmic web we observe today. But the opposite happened in underdense regions. Places that started with slightly less matter than average lost even more over time. Their weaker gravity couldn't hold onto material as effectively. Matter flowed out toward the denser regions, drawn by stronger gravitational pull. These underdense regions became emptier and emptier, eventually becoming voids. The Boötes Void was one of these slightly underdense regions in the primordial universe. 13 billion years ago, it wasn't particularly special. Just a region where the density was perhaps 0.001% below average. But over all that time, gravity has been steadily evacuating it, pulling matter outward towards the surrounding cosmic web. The void has been growing, expanding, becoming ever more empty, and this process continues today. The Boötes Void is still growing, still expanding, still losing what little matter it has to the denser regions that surround it. Those 60 galaxies that remain inside the void are slowly, imperceptibly drifting toward the edges, drawn by gravitational attraction from outside. Billions of years from now, the void will be even larger and even emptier than it is today. The galaxies inside it may have migrated entirely to the walls, leaving the interior a perfect vacuum of nothingness. But here's something remarkable. The Boötes Void isn't alone. It isn't even unusual. It's not the largest void astronomers have discovered, just the most famous because it was one of the first to be identified. The universe is filled with voids. They're everywhere. When astronomers map the three-dimensional distribution of galaxies across the cosmos, they find a structure that looks almost like a sponge or a honeycomb. Galaxies cluster along filaments and walls, forming an intricate web of matter. But between these filaments, filling most of the universe's volume, are the voids. Some estimates suggest that voids make up roughly 80% of the universe's volume. That's a staggering number. It means that most of space is empty. Most of the cosmos is cold. The galaxies and stars and planets that we find so fascinating, the matter that makes up everything we can see and touch, occupies only about 20% of the universe's volume. The rest is void. The largest void potentially identified is sometimes called the Giant Void, or the Giant Void in Canis Venatici, and it might span up to 500 million light-years. That's even larger than the Boötes Void. But the boundaries of voids are fuzzy and difficult to define precisely. Where does a void end and the surrounding cosmic web begin? The transition is gradual, not sharp. Different astronomers using different methods might draw the boundaries in different places. There's also the mysterious cold spot, a region of the cosmic microwave background that's slightly colder than its surroundings. This cold spot was discovered in 2004 in data from NASA's WMAP satellite. It's about 5 billion light-years from Earth and spans a region of sky roughly 5 degrees across. One explanation for the cold spot is that it represents a super void, an enormous empty region along the line of sight that has left an imprint on the cosmic microwave background. The light from the Big Bang, passing through this super void, would lose a tiny amount of energy, making that region appear slightly cooler. If this explanation is correct, The supervoid causing the cold spot might be among the largest structures in the observable universe. These cosmic voids are so large that they challenge our ability to comprehend them. They're not just empty spaces between galaxies like the space between houses in a neighborhood. They're fundamental features of the universe's architecture, as important to cosmic structure as the galaxies themselves. Without voids, there would be no cosmic web. Without emptiness, there would be no structure at all. The universe would be a uniform soup of matter, undifferentiated and featureless. It's the contrast between dense regions and voids that gives the cosmos its character. What would happen to a human being exposed to the conditions inside the Boötes Void? The question seems absurd because no human will ever go there. Even traveling at the speed of light, which is impossible for anything with mass, it would take 700 million years to reach the void from Earth. That's longer than complex life has existed on our planet. By the time you arrived, if you could somehow make the journey, Earth's sun would have burned through most of its hydrogen fuel and would be approaching the end of its life. But as a thought experiment, the question is instructive. It helps us understand what the cold of the void actually means. In the vacuum of space, without a spacecraft, you would die almost immediately. But not from cold, at least not at first. This is counterintuitive. We think of space as cold, and it is cold, but the immediate danger isn't freezing. The immediate danger is the vacuum itself. On Earth, you're constantly surrounded by air at a pressure of roughly 1 atmosphere. This pressure keeps the gases in your blood dissolved. It keeps your lungs inflated. It keeps your body functioning normally. In a vacuum, all of that changes. Without external pressure, the gases in your blood would begin to bubble out, like opening a shaken soda bottle. Your lungs would try to expand against nothing. You would lose consciousness within about 15 seconds due to lack of oxygen reaching your brain. Heat. Transfer in a vacuum is also different from what we experience on Earth. In air or water, heat transfers through conduction and convection. Fast-moving molecules bump into slower-moving molecules, transferring energy. This is why wind makes a cold day feel colder. The moving air carries heat away from your body quickly, but in a vacuum, there are no molecules to carry heat away. The only way to lose heat is through radiation, emitting infrared light that carries energy into space. This process is much slower than conduction or convection. So, in the immediate aftermath of exposure to the void, you wouldn't freeze, you would suffocate, you would die from lack of oxygen, and from the violence of sudden decompression long before the cold claimed you. But eventually, if your body remained in the void, it would cool. Over hours and days, it would radiate its heat into the surrounding space. Slowly, incrementally, the temperature would drop. Your body would approach equilibrium with its surroundings. Eventually, after perhaps a few days, it would reach the ambient temperature of 2.7 Kelvin. At that point, your body would be frozen in a way that no temperature on Earth could achieve. Every molecule would be nearly still. Every atom would be approaching its minimum energy state, vibrating only with the irreducible quantum jitter that physics demands. Your body would be as close to perfect preservation as the laws of physics allow. Not dead in the ordinary sense, but suspended, motionless, a monument to the cold of the cosmos. This leads to a philosophical question that has intrigued scientists and thinkers for decades. Is the cold of space really cold? Or is it just an absence of heat? The distinction matters more than you might think. On Earth, we experience cold as something active, almost aggressive. We say the cold bites, We say it penetrates our clothing. We say it chills us to the bone. Our language treats cold as a thing, an entity, a force that acts upon us. But that's not really what's happening physically. Cold doesn't flow into us. Heat flows out of us. When we feel cold, we're feeling our own body heat escaping into our surroundings. Cold is not a thing. It's the absence of a thing. It's what remains when heat is removed. In the Boötes Void, there's almost no heat to begin with. The cosmic microwave background provides a tiny amount of energy, but it's negligible compared to what we experience on Earth. The temperature is already at the cosmic minimum. There's nothing pulling heat out of you more than anywhere else in the universe. The void represents something close to the absence of heat on the largest possible scale. It's not that something cold is there, it's that warmth is almost entirely absent. And that distinction, while subtle, is profound. It means that the cold of the void is not something hostile or aggressive in the way we typically imagine cold. It's simply emptiness. It's nothing. It's the great nothing. And yet, even in this nothing, things exist. Those 60 galaxies inside the Boötes Void, scattered though they are, each contain billions of stars. Those stars have planets. Those planets have moons. And on some of those worlds, for all we know, life might have emerged. Evolution might have produced intelligent beings. Civilizations might have risen and perhaps fallen. Think about what their experience of the universe would be like. Life in the Boötes Void would look out at a night sky almost entirely devoid of other galaxies. They would see their own stars, their own world, their own cosmic neighborhood, but beyond that, almost nothing. The nearest galaxy might be so distant that their ancestors never detected it until they developed the most powerful telescopes. They might have believed for most of their history that their galaxy was alone in the universe, an island of matter in an infinite sea of nothing. They would have every reason to think they were alone. And in a practical sense, they might be right. The distances separating them from any other civilization, if any exists in the void, would be measured in tens of millions of light years. Communication would be impossible on any reasonable timescale. Even light would need millions of years to carry a message from one galaxy to another. They would be isolated in a way that we, living in a relatively crowded region of the cosmos, can barely imagine. The study of voids like Boötes has become an important part of modern cosmology. Far from being boring empty spaces, voids tell us crucial things about the universe. They tell us about the initial conditions that existed shortly after the Big Bang, about those tiny density fluctuations that seeded all cosmic structure. By measuring the sizes and shapes of voids, we can constrain the statistical properties of the primordial fluctuations, learning about physics that operated in the first fraction of a second of cosmic history. Voids also tell us about dark energy, the mysterious force causing the universe's expansion to accelerate. Dark energy affects voids differently than it affects dense regions. In dense regions, gravity dominates, pulling matter together and slowing the expansion. But in voids, there's almost no matter, and dark energy's influence is more pronounced. Voids expand faster than the universe as a whole. By studying how voids grow and evolve over cosmic time, we can measure the properties of dark energy with remarkable precision. Astronomers have developed sophisticated techniques to map voids across the cosmos. Large-scale redshift surveys like the Sloan Digital Sky Survey have catalogued millions of galaxies, allowing scientists to construct three-dimensional maps of the universe's structure. These maps reveal the cosmic web in stunning detail, showing where matter concentrates and where it's absent. The voids stand out clearly as regions of significantly reduced galaxy density, spherical or elongated bubbles, surrounded by walls and filaments of galaxies. One fascinating discovery is that voids aren't completely random in their distribution. They tend to be roughly similar in size, with typical diameters of about 50 to 100 million light-years. This characteristic size reflects the physics of how structures formed in the early universe. Smaller voids tend to merge into larger ones over time, while larger voids grow as matter continues to drain toward the surrounding dense regions. The Boötes Void, at 330 million light-years across, is exceptionally large, several times bigger than typical voids. This makes it particularly valuable for studying extreme cosmic environments. In a sense, the emptiest places in the universe are telling us the most about its ultimate fate. The cold of the Boötes Void isn't just a curiosity, it's a window into the fundamental physics that governs everything. Now let's go deeper. Let's descend into the physics of cold itself, into the strange realm where temperature begins to lose its familiar meaning, and the universe operates by rules that seem almost alien to everything we experience in our daily lives. Because the Boötes Void, as remarkably cold as it is, hovering near that 2.7 Kelvin baseline of the cosmic microwave background, is not actually the coldest place we know of. There are places, both natural and artificial, that have achieved temperatures even lower. And what happens at those temperatures reveals something fundamental about the nature of reality itself. To truly understand cold at its most extreme, we first need to revisit what temperature actually measures. I mentioned earlier that temperature is related to the motion of particles, but that's a simplification, a useful approximation for everyday understanding. The full story is more nuanced, more precise, and ultimately more beautiful. Temperature is related to the average kinetic energy of particles in a system. Kinetic energy is the energy of motion. It's what a moving object possesses simply by virtue of moving. A speeding car has kinetic energy. A thrown baseball has kinetic energy. An atom vibrating in a crystal has kinetic energy. The faster something moves, the more kinetic energy it has. When we measure temperature, we're measuring the average kinetic energy of all the countless particles that make up whatever substance we're examining. In a hot gas, molecules are zooming around at tremendous speeds, hundreds or thousands of meters per second, colliding with each other and with the walls of their container, bouncing off in random directions, carrying energy from place to place. In a cold gas, those same molecules are moving more slowly, carrying less energy, colliding less violently. In a solid at room temperature, atoms vibrate in place, oscillating back and forth around their equilibrium positions in the crystal structure. Cool the solid down, and those vibrations become smaller, slower, less energetic. The atoms move less. Temperature drops. This connection between temperature and motion seems to suggest that at absolute zero, at 0 Kelvin, particles would stop moving entirely. They would have zero kinetic energy, zero motion, perfect stillness, and in classical physics, the physics that governs our everyday experience, this is exactly what we'd expect. Cool something down to absolute zero, and everything stops. But here's where quantum mechanics enters the picture and changes everything. Quantum mechanics forbids perfect stillness. It's not just difficult to achieve zero motion, it's fundamentally impossible. The universe contains a built-in minimum amount of jitter, a floor beneath which nothing can descend. Even at absolute zero, particles aren't completely motionless. They vibrate, fluctuate, shimmer with a residual energy that can never be removed. This irreducible energy is called zero-point energy. It arises from one of the most famous principles in quantum mechanics, Heisenberg's uncertainty principle. Werner Heisenberg showed in 1927 that you cannot simultaneously know both the position and the momentum of a particle with perfect precision. The more precisely you know where a particle is, the less precisely you can know how fast it's moving, and vice versa. This isn't a limitation of our measuring instruments. It's a fundamental property of nature. The universe simply doesn't have definite values for both position and momentum at the same time. The uncertainty principle has a remarkable consequence for cold. If a particle were perfectly still, we would know its momentum exactly. It would be zero. But if the momentum is exactly zero, the uncertainty principle demands that the position be completely undefined, spread out over all of space. A particle that's truly motionless would have to be everywhere at once. Since particles are clearly located in specific regions of space, they must have some momentum. They must be moving at least a little bit. They can never be perfectly still. This is why you can never actually reach absolute zero. You can approach it. You can get tantalizingly, exquisitely close. Scientists have achieved temperatures measured in billionths of a Kelvin. Temperatures so close to absolute zero that the difference seems almost meaningless. But you can never quite arrive. There's always that quantum jitter, that zero-point energy, that irreducible motion that refuses to be removed, no matter how sophisticated your cooling techniques become. The cosmic microwave background at 2.7 Kelvin sets a natural floor for temperatures throughout most of the universe. Any object floating in the void of space will eventually reach thermal equilibrium with the CMB, absorbing microwave radiation and warming to that baseline temperature. You might think this means nothing can be colder than 2.7 Kelvin naturally, but that's not quite true. The CMB floor assumes equilibrium. It assumes that an object has been sitting in empty space long enough to reach balance with the surrounding radiation. But there are situations where objects can be colder than their surroundings, at least temporarily. And one of these situations occurs in a remarkable place called the Boomerang Nebula. The Boomerang Nebula is located about 5,000 light-years from Earth in the southern constellation Centaurus. Through a telescope, it appears as a distinctive bow-tie shape, two lobes of gas extending in opposite directions from a central star. It's a planetary nebula, which, despite the name, has nothing to do with planets. Planetary nebulae are clouds of gas and dust ejected by dying stars. When a star like our Sun exhausts its nuclear fuel, it swells into a red giant and then expels its outer layers into space, creating an expanding shell of gas that glows as it's ionized by ultraviolet light from the dying stellar core. But the Boomerang Nebula is no ordinary planetary nebula. The gas it contains is expanding with extraordinary speed, moving outward at about 164 kilometers per second. That's almost 600,000 kilometers per hour. The gas is racing away from the central star far faster than in typical planetary nebulae, and this rapid expansion has a remarkable consequence. When a gas expands rapidly without absorbing heat from its surroundings, it cools. This is called adiabatic cooling, and it's the same principle that makes the air coming out of a spray can feel cold against your skin. Inside the pressurized can, the gas is at high pressure and relatively high temperature. When you press the nozzle and the gas expands into the room, it does work against the surrounding atmosphere, pushing air molecules out of the way. This work requires energy, and that energy comes from the thermal motion of the gas molecules themselves. They slow down, the gas cools. The same thing happens in the Boomerang Nebula, but on a cosmic scale. The gas is expanding so rapidly, doing so much work against its surroundings, that it has cooled below the temperature of the cosmic microwave background. Measurements made with the Atacama Large Millimeter Array and other radio telescopes indicate that parts of the Boomerang Nebula have cooled to about 1 Kelvin, 1 degree above absolute zero, colder than the cosmic background radiation, colder than the void between galaxies, colder than anywhere else we've measured in the natural universe. Think about what this means. The Boomerang Nebula is colder than the Boötes Void, colder than the vast emptiness between superclusters. A dying star, expelling its outer layers in a final cosmic gasp, has inadvertently created the coldest natural place known to science. It's a remarkable example of how astrophysical processes can produce conditions more extreme than even the emptiest voids of space. The temperature difference between the Boomerang Nebula and the cosmic background is relatively small, only about 1.7 Kelvin, but it represents something unexpected. In most of the universe, you simply can't get colder than the CMB. The background radiation is everywhere, constantly pumping a tiny amount of energy into everything it touches. But here, through the physics of rapid expansion, through the thermodynamics of adiabatic cooling, nature has found a way to beat the background. The nebula is absorbing energy from the CMB, but it's losing energy through expansion faster than the CMB can replenish it. The result is a pocket of cold in an already cold universe, a record holder for natural low temperatures. The Boomerang Nebula won't remain this cold forever. Eventually, the expanding gas will slow down as it encounters the thin interstellar medium surrounding it. The adiabatic cooling will cease. The gas will gradually warm back up, absorbing energy from the cosmic microwave background until it reaches equilibrium at 2.7 Kelvin. The coldest natural place will disappear, merge back into the ambient hum of the universe's background temperature. The record will be lost. But for now, for this brief cosmic moment lasting perhaps a few thousand years, the Boomerang Nebula holds the title, the coldest natural place that exists. But humans have achieved temperatures far colder than even the Boomerang Nebula. In laboratories on Earth, using sophisticated cooling techniques developed over more than a century of research, scientists have reached temperatures measured in billionths of a Kelvin. These experiments push against the very limits of what's physically possible, approaching absolute zero with precision that would have seemed magical to scientists just a few generations ago. The journey to extreme cold began in the late 19th century with the liquefaction of gases. Scientists discovered that by compressing gases and then allowing them to expand, they could achieve progressively lower temperatures. Oxygen was liquefied in 1883 at about 90 Kelvin. Nitrogen followed at 77 Kelvin. Hydrogen was liquefied in 1898 at 20 Kelvin. Each success pushed the frontier of cold further toward absolute zero. The final common gas to be liquefied was helium. Helium is extraordinarily difficult to condense because its atoms interact so weakly with each other. It took until 1908 for Dutch physicist Heike Kamerlingh-Onnes to succeed in liquefying helium at about 4 Kelvin. This achievement won him the Nobel Prize and opened the door to a new realm of physics. Liquid helium became the gateway to temperatures just a few degrees above absolute zero. But 4 Kelvin wasn't cold enough for some experiments. Scientists wanted to go colder. They developed techniques like evaporative cooling, where you allow the fastest molecules in a liquid to escape, leaving behind slower, colder molecules. They invented dilution refrigerators, which use mixtures of helium-3 and helium-4 to achieve temperatures in the millikelvin range, thousandths of a degree above absolute zero. They created laser cooling techniques, using carefully tuned laser light to slow atoms down to speeds measured in centimeters per second, achieving temperatures in the microkelvin range, millionths of a degree above absolute zero. And they didn't stop there. Magnetic cooling techniques, which exploit the quantum properties of atomic spins, have achieved temperatures in the nanokelvin range, billionths of a degree above absolute zero. The current record for the coldest temperature achieved in a laboratory is in the tens of picokelvin range, trillionths of a degree above absolute zero. At this temperature, atoms are moving so slowly that they would take hours to cross a human hair. They're essentially frozen, hovering in place with only that irreducible quantum jitter to indicate they're not perfectly still. At these extreme temperatures, matter behaves in ways that have no analog in everyday experience. Quantum effects, which are normally invisible at ordinary temperatures, become dominant and observable. The weird, counterintuitive predictions of quantum mechanics manifest directly in the behavior of matter. One of the most famous phenomena that occurs at extremely low temperatures is the Bose-Einstein condensate. This exotic state of matter was predicted theoretically by Albert Einstein and Indian physicist Satyendra Nath Bose in the 1920s, but it wasn't achieved experimentally until 1995, when Eric Cornell and Carl Wieman at the University of Colorado succeeded in cooling a gas of rubidium atoms to about 170 nanokelvin. In a Bose-Einstein condensate, something extraordinary happens. At ordinary temperatures, atoms in a gas are distinct individuals. Each atom has its own position, its own velocity, its own identity. They bounce around independently, occasionally colliding but generally doing their own thing. But as you cool the gas down, as you remove thermal energy and the atoms slow to a crawl, quantum effects begin to dominate. The atoms start to lose their individual identities. In quantum mechanics, particles are described by wave functions, mathematical objects that encode the probability of finding a particle in a particular place with a particular momentum. At high temperatures, the wave functions of different atoms are compact and well separated. Each atom is localized in its own region of space. But as the temperature drops, the wave functions spread out. They become larger and more diffuse. Eventually, they start to overlap. When the wave functions overlap sufficiently, something remarkable happens. For a particular type of particle called bosons, which include atoms with an even number of protons and neutrons, the overlapping particles can all fall into the same quantum state. They merge. They become indistinguishable, not just in principle, but in practice. The thousands or millions of atoms in the condensate stop behaving as separate particles and start behaving as a single quantum entity. They act as one. Bose-Einstein condensates exhibit quantum behavior on a macroscopic scale, visible to the naked eye or at least to ordinary cameras. You can photograph them. You can watch them evolve. You can see quantum mechanics in action, not hidden in the subatomic realm, but displayed openly in a cloud of atoms a millimeter across. These condensates have remarkable properties. They can flow without friction, a phenomenon called superfluidity. In a superfluid, there's no viscosity, no resistance to flow. As superfluid helium can climb up the walls of its container, defying gravity. It can flow through tiny pores that would block ordinary liquids. It can circulate indefinitely without slowing down, maintaining motion that would dissipate almost instantly in any normal fluid. Bose-Einstein condensates can also exhibit quantum tunneling on a collective scale. Individual particles can tunnel through barriers that would be impassable according to classical physics, appearing on the other side without ever existing in the barrier itself. In a condensate, this tunneling can happen coherently, with all the atoms tunneling together as a single entity. The implications for future technologies are profound and still being explored. The coldest natural places in the universe, the voids between galaxies, and even the Boomerang Nebula are not cold enough to create Bose-Einstein condensates naturally. At 2.7 Kelvin, or even at 1 Kelvin, there's still too much thermal energy. Atoms still move too fast. Their wave functions remain compact enough to keep them separate and individual. Bose-Einstein condensation typically requires temperatures below a microkelvin, millionths of a degree above absolute zero. Only in the artificial environments of Earth's laboratories, shielded from the cosmic microwave background, cooled by sophisticated machinery, can these exotic states of matter be achieved. Another remarkable phenomenon that emerges at low temperatures is superconductivity. In 1911, just 3 years after liquefying helium, Heike Kamerlingh-Onnes made another astonishing discovery. When he cooled mercury below about 4 Kelvin, its electrical resistance suddenly dropped to zero. Not almost zero, exactly zero. Electricity could flow through the mercury without any loss whatsoever, without generating any heat, without dissipating any energy. This was unprecedented. In normal conductors like copper wire, electricity always encounters some resistance. The flowing electrons collide with atoms in the metal, transferring energy, generating heat. This is why wires get warm when current flows through them. This is why electrical transmission over long distances loses significant amounts of energy. Resistance is everywhere in normal materials, but in a superconductor, resistance vanishes completely. An electrical current started in a superconducting loop will continue flowing indefinitely, without diminishing, without requiring any power input to maintain it. Experiments have monitored superconducting currents for years, without detecting any decay. As far as we can tell, they would continue forever. Superconductivity also expels magnetic fields from the interior of the material, a phenomenon called the Meissner effect. A superconductor will actively push magnetic field lines out of itself, becoming perfectly diamagnetic. This is why superconductors can levitate above magnets, suspended in midair by the interaction between the expelled magnetic field and the magnet below. You've probably seen photographs of this magnetic levitation. It's one of the most striking visual demonstrations of quantum effects in action. Superconductivity has enormous practical applications. The powerful magnets in MRI machines are superconducting electromagnets, cooled by liquid helium to maintain their resistance-free current. The Large Hadron Collider at CERN uses superconducting magnets cooled to 1.9 Kelvin to bend the paths of particles, traveling at nearly the speed of light. Future technologies might include superconducting power lines that transmit electricity without loss, superconducting computers that generate no heat, superconducting motors with perfect efficiency. But achieving the temperatures required for superconductivity is challenging and expensive. Most conventional superconductors require temperatures below about 30 Kelvin. Maintaining these temperatures requires sophisticated cooling systems and significant energy input. This is why superconducting technologies remain specialized, used only where their unique properties justify the cost and complexity of keeping them cold. In the 1980s, scientists discovered materials that superconduct at higher temperatures, sometimes above 100 Kelvin. These high-temperature superconductors can be cooled with liquid nitrogen rather than liquid helium, which is much cheaper and more practical. But even 100 Kelvin is still extremely cold by everyday standards, about minus 173 degrees Celsius. We're still far from room temperature superconductors, though research continues and occasional breakthroughs offer hope. The quest to achieve ever colder temperatures continues to drive innovation in physics and engineering. Researchers are developing new cooling techniques that might eventually allow us to explore quantum phenomena at scales previously impossible. Cold atom physics, where atoms are cooled to nanokelvin temperatures and manipulated with lasers, has already led to breakthroughs in precision measurement, including atomic clocks accurate to 1 second in billions of years. These clocks are so precise that they can detect the tiny differences in time caused by gravity, confirming predictions of Einstein's general relativity. Quantum computers, which promise to revolutionize computing by exploiting the strange rules of quantum mechanics, require extremely cold temperatures to operate. The quantum bits, or qubits, that store and process information must be isolated from thermal noise, which means cooling them to temperatures measured in millikelvin. Companies and research institutions around the world are racing to build practical quantum computers, and the cold is essential to their success. The coldest places in the universe, the voids between galaxies, will never be laboratories we can visit, but they serve as reminders of what extreme cold means, what happens to matter when thermal energy is stripped away, and what the universe will eventually become. The physics we develop to create cold on Earth connects us to the cold that exists naturally in the cosmos, a bridge between human technology and cosmic reality. The physics of extreme cold connects to the deepest questions about the nature of reality. At temperatures near absolute zero, the quantum nature of matter becomes impossible to ignore. Particles exist as probability waves spread out in space rather than localized at specific points. The boundary between particle and wave blurs, and sometimes disappears entirely. The deterministic, predictable world of classical physics gives way to the probabilistic, uncertain world of quantum mechanics. This is why physicists are so fascinated by cold. Not merely because cold has practical applications, though it certainly does. Not merely because cold allows technological feats that would otherwise be impossible, but because cold reveals the fundamental nature of reality that's hidden at higher temperatures. The quantum world is always there, underlying everything, but at ordinary temperatures, thermal noise masks it. Random jiggling drowns out the subtle quantum effects. Heating something is like adding static to a radio signal. The information is still there, but it becomes harder to detect. Cooling. Something is like removing the static. The quantum signal emerges clearly, undisturbed by thermal noise. What quantum effects might occur in the cold of the Boötes Void? The truth is, the void isn't quite cold enough for the most dramatic phenomena. At 2.7 Kelvin, there's still enough thermal energy to prevent Bose-Einstein condensation in most materials. Atoms still have enough kinetic energy to behave more or less classically, bouncing around and colliding like tiny billiard balls, rather than merging into collective quantum states. The void is cold, extraordinarily cold, but not cold enough for the really exotic physics. Still, some quantum effects would become noticeable in the void. Chemical reaction rates depend strongly on temperature, and many reactions would slow to imperceptible crawls. Materials would behave differently than they do at ordinary temperatures. Metals would become superconductors if they could somehow be cooled just a bit more. Gases would condense into liquids and solids far more readily. The physics of the void, while not as exotic as a laboratory at nanokelvin temperatures, would still be subtly different from anything we experience on Earth. There's also the question of dark matter and its relationship to cold. We believe that approximately 85% of all matter in the universe is dark matter, an invisible substance that doesn't interact with light or ordinary matter except through gravity. We can't see dark matter directly, but we can detect its gravitational influence on galaxies and galaxy clusters. Without dark matter, galaxies would fly apart. Their visible stars don't contain nearly enough mass to hold them together gravitationally. Something else must be there, something invisible, providing the gravitational glue. Dark matter is thought to be cold in the cosmological sense. This doesn't mean dark matter is at a low temperature like an ice cube. It means dark matter particles are moving slowly compared to the speed of light. In the early universe, particles were moving at tremendous velocities, close to light speed. As the universe expanded and cooled, most particles slowed down. Dark matter particles, whatever they are, appear to have been moving slowly even early on, or else slowed down quickly. This cold dark matter model is the foundation of our understanding of cosmic structure formation. It explains why galaxies and clusters formed the way they did, why the cosmic web has the structure it has, why voids like the Boötes Void exist at all. The voids in the universe are underdense in dark matter as well as in ordinary visible matter. The Boötes Void contains less dark matter than average, which is part of why it's so empty of galaxies. Dark matter provides the gravitational scaffolding on which ordinary matter accumulates. Where dark matter is dense, ordinary matter falls in and forms galaxies. Where dark matter is sparse, ordinary matter has nothing to cling to. It drifts away, drawn toward denser regions, leaving voids behind. The cold of the Boötes Void is connected to the cold of dark matter in this deep, cosmological sense. Let me also tell you about the remarkable history of how we came to understand the speed of light and its connection to temperature. In the late 17th century, most scientists assumed light traveled instantaneously. You opened your eyes and you saw things immediately. So it seemed like light must be instantaneous. But in 1676, a Danish astronomer named Ole Rømer made a careful observation of Jupiter's moons and noticed something strange. The times when the moons disappeared behind Jupiter varied depending on where Earth was in its orbit. When Earth was closer to Jupiter, the eclipses happened earlier than predicted. When Earth was farther from Jupiter, they happened later. Rømer realized this was because light took time to travel the different distances. He calculated that light took about 22 minutes to cross the diameter of Earth's orbit. His calculation wasn't quite right, because he didn't know the exact size of Earth's orbit. but he proved that light has a finite speed. Today, we know the speed of light with extraordinary precision. We've measured it using lasers, atomic clocks, and sophisticated equipment. We've confirmed that it's constant, that it doesn't change depending on how fast you're moving or where you are. And we've discovered that this speed, this constant, is woven into the very fabric of the universe. Let's take a final journey now. Let's leave the present behind and travel forward through time, deep into the future, into the cold that awaits not just the Boötes Void, but everything that exists. Because the coldest places in the universe today, those vast empty regions hovering at 2.7 Kelvin, are merely a preview, a glimpse, a hint of what's coming. The real cold, the ultimate cold, the cold that will eventually claim all stars, all galaxies, all planets, all life lies ahead. And understanding this cold means understanding the fate of the cosmos itself. The universe is expanding. This fundamental truth has been known since the 1920s, when American astronomer Edwin Hubble made one of the most important observations in the history of science. By studying distant galaxies and measuring the shift in their light toward the red end of the spectrum, Hubble discovered that nearly every galaxy is moving away from us. And the farther away a galaxy is, the faster it's receding. This wasn't because the Milky Way is at the center of some cosmic explosion with everything flying away from us. It's because space itself is stretching. The fabric of the universe is expanding, carrying galaxies apart like dots painted on the surface of an inflating balloon. For most of the 20th century, cosmologists assumed that this expansion would eventually slow down. After all, gravity is attractive. Every bit of matter in the universe pulls on every other bit. All those galaxies, all that dark matter should be collectively tugging on the cosmos, acting like a brake on the expansion. Maybe the expansion would slow gradually, approaching some equilibrium state. Maybe it would reverse entirely, leading to a big crunch where everything collapses back together in a mirror image of the Big Bang. The future of the universe seemed to depend on how much matter it contained, and whether gravity was strong enough to overcome the expansion. But in 1998, two independent teams of astronomers made a discovery that changed everything we thought we knew about cosmic fate. They were studying a particular type of a stellar explosion called a Type Ia supernova. These supernovae are special because they all have roughly the same intrinsic brightness. They're what astronomers call standard candles. By measuring how bright a Type Ia supernova appears from Earth, and comparing that to how bright it actually is, you can calculate how far away it is. And by measuring the redshift of its host galaxy, you can determine how fast it's moving away from us. What the astronomers expected to find was that very distant supernovae would be brighter than expected. If the expansion of the universe was slowing down, distant galaxies wouldn't have moved as far away as a simple calculation would suggest. The supernovae in those galaxies would be closer than expected, and therefore brighter. But that's not what they found. The distant supernovae were dimmer than expected. The galaxies hosting them were farther away than they should have been. The expansion of the universe wasn't slowing down at all. It was speeding up. Something was pushing the cosmos apart, overcoming the gravitational attraction of all the matter in the universe, accelerating the expansion instead of breaking it. We call this mysterious something dark energy. Though the name is more an admission of ignorance than a description, we don't know what dark energy is. We don't know why it exists. We can't detect it directly. We can only infer its presence from its effect on the expansion of space, and that effect is enormous. Dark energy makes up about 68% of the total energy content of the universe. It's the dominant component of cosmic reality. Ordinary matter, the stuff that makes up stars and planets and people, is only about 5%. Dark matter is about 27%. Dark energy is everything else, and it's winning. The discovery of dark energy earned the two teams the Nobel Prize in Physics in 2011. But it also fundamentally altered our understanding of the universe's future. If dark energy continues to dominate, and there's no evidence that it will stop, the expansion of the universe will continue to accelerate forever. Galaxies will fly apart faster and faster. The distances between cosmic structures will grow exponentially, and eventually the consequences will become truly profound. As the universe expands, light from distant galaxies takes longer and longer to reach us. The photons have to traverse ever greater distances, traveling through a cosmos that's stretching even as they fly. Eventually, some galaxies will be receding so fast that their light will never reach us at all. Space will be expanding between us and them faster than light can cross it. This doesn't violate the cosmic speed limit because the galaxies aren't moving through space faster than light. Space itself is expanding, carrying the galaxies with it. But the practical effect is the same. Those galaxies will pass beyond our cosmic horizon, vanishing from the observable universe forever. In about 100 billion years, astronomers in whatever remains of the Milky Way will look out at the night sky and see almost nothing. The other galaxies will have disappeared from view, carried away by the relentless expansion of space. The cosmic web, that intricate structure of filaments and walls and voids that characterizes our current universe, will be invisible. Only the local group, our immediate cosmic neighborhood, will remain accessible. Everything else will have receded beyond the horizon, forever unreachable, forever unknown. Those future astronomers might not even know that other galaxies ever existed. They might look out at the darkness and conclude that their galaxy is the only one, a single island of stars in an infinite empty void. The cosmic microwave background, that crucial evidence for the Big Bang, will have stretched to wavelengths so long that it will be undetectable. The evidence for the universe's hot, dense beginning will have faded away. Future civilizations might have no way of knowing that the universe was ever different from the cold, empty state they observe. And as the universe expands, it cools. This is the same principle we discussed earlier, the same adiabatic cooling that makes expanding gases lose temperature. The cosmic microwave background, currently at 2.7 Kelvin, will continue to drop. In 1 trillion years, it might be at 1 millionth of a Kelvin. In 10 trillion years, even less. The radiation that fills all of space, the faint afterglow of creation, will become fainter and fainter, colder and colder, approaching but never quite reaching absolute zero. The voids, already the coldest places in the universe, will cool along with everything else. The Boötes Void will see its temperature drop from 2.7 Kelvin to 2 Kelvin to 1 Kelvin to fractions of a Kelvin so small that writing them out would require scientific notation. The void will remain what it is, an underdense region in the cosmic web, but the distinction will matter less and less as everything approaches the same cold equilibrium, and the voids will grow. As the universe expands, the filaments and walls of galaxies will spread out. The dense regions will become less dense. The voids will expand, swallowing the cosmic web. growing to encompass volumes that dwarf even the current Boötes Void. Eventually, most of space will be void-like. Most of the universe will be empty and cold and dark. The cosmic web will dissolve into a thin haze of matter scattered through an incomprehensibly vast volume of space. But what about the stars? Stars are the universe's furnaces. They produce heat and light through nuclear fusion, converting hydrogen into helium and releasing tremendous amounts of energy in the process. As long as stars exist, they will warm their surroundings. They will provide the energy that powers planets, that drives weather and chemistry, that makes life possible. The cold of deep space won't reach the planets that orbit stars, at least not while those stars still burn. But stars don't last forever. The fuel that powers them, primarily hydrogen, is finite. Every second, our sun converts about 600 million tons of hydrogen into helium. It's been doing this for 4.5 billion years, and it has enough fuel to continue for another 5 billion years or so. But eventually, it will run out. The hydrogen in its core will be exhausted. The sun will swell into a red giant, engulfing Mercury and Venus, and possibly Earth, before shedding its outer layers and fading into a white dwarf, a dense stellar remnant slowly cooling over billions of years. Massive stars burn through their fuel even faster. A star 10 times the mass of the sun might live only 10 million years before exploding as a supernova. These brief, brilliant lives end in cataclysmic death, scattering heavy elements through space, but leaving behind neutron stars or black holes that produce almost no light. The smallest stars, the red dwarfs, are the opposite. They burn their fuel so slowly that they can last for trillions of years. Red dwarfs are incredibly efficient, converting their hydrogen to helium at a leisurely pace, producing just enough energy to glow faintly, but steadily for timescales that dwarf the current age of the universe. A red dwarf born today might still be shining when the universe is 100 trillion years old. Red dwarfs are also the most common type of star. About 70% of all stars in the Milky Way are red dwarfs, but they're all so dim that none of them are visible to the naked eye despite being relatively common. When you look up at the night sky, every star you can see with your naked eye is either larger and brighter than the sun, or it's not a star at all, but a planet. The last stars in the universe will be the smallest red dwarfs. These tiny suns, perhaps only 8% of the sun's mass, will burn for 100 trillion years or more. For perspective, the universe is currently about 14 billion years old. The last red dwarfs will shine for a time roughly 10,000 times longer than the current age of the cosmos. They will witness eras we can barely imagine, cosmic epochs so distant that our current universe would be forgotten history, a brief flash at the beginning of things. But eventually, even the last red dwarfs will exhaust their fuel. Their cores will contract. The nuclear fires will go out. They will become black dwarfs, stellar remnants composed of degenerate matter, slowly cooling toward the ambient temperature of space. Black dwarfs don't actually exist yet in our universe. The cosmos isn't old enough for any white dwarf to have cooled to that state. But in the far future, trillions upon trillions of years from now, black dwarfs will be common. They'll be all that remains of the stars that once illuminated the cosmos. When the last stars die, the universe will enter what astronomers call the degenerate era, sometimes called the black dwarf era. There will be no more light, no more heat from nuclear fusion, no more warmth except for the fading radiation of cooling remnants. White dwarfs will continue to glow faintly for a while, radiating the heat stored in their cores. Neutron stars will spin down and cool, but these sources of energy are finite. They will fade. The universe will grow dark. This era will last for an almost unimaginably long time. The timescales involved make everything we've discussed so far seem brief by comparison. We're talking about 10 to the 37th power years, 10 to the 40th power years, numbers so large that they're essentially meaningless to human intuition. The total amount of time that stars have been shining in our universe, about 13 billion years, is nothing compared to the dark eons that follow. The degenerate era will be a trillion times longer than the age of stars. During this era, the Boötes Void will no longer be special. All of space will be equally cold, equally empty, equally dark. The distinction between void and filament that characterizes our current universe will have disappeared. There will be no galaxies, no stars, no light, just dead stellar remnants, slowly cooling, drifting through an ever-expanding cosmos, approaching equilibrium with the cosmic background radiation that will by then be so cold it's almost indistinguishable from absolute zero. The temperature of the universe during the degenerate era will be almost unimaginably close to absolute zero. Perhaps a billionth of a Kelvin, perhaps a trillionth, perhaps even less. At these temperatures, quantum effects will dominate completely. Any matter that still exists will behave in ways utterly alien to our everyday experience. The universe will be a cold, dark, quantum realm, nothing like the warm, bright cosmos we inhabit today. But even the degenerate era is not the end. In the far, far future, even the dead stellar remnants will decay. This brings us to one of the most speculative but fascinating areas of physics, the ultimate fate of matter itself. Protons, the positively charged particles at the heart of atoms, were once thought to be completely stable. They don't decay through ordinary processes. A proton sitting in isolation would last forever, according to classical physics. But some extensions of the standard model of particle physics predict that protons might not be truly stable. They might decay through exotic quantum processes, transforming into lighter particles and radiation over incredibly long timescales. The predicted lifetime of a proton, if it decays at all, is somewhere around 10 to the 34th power years or longer. This is so much greater than the current age of the universe that proton decay has never been observed. Experiments have watched enormous quantities of protons for decades without detecting a single decay. But in the far future, over timescales of 10 to the 40th power years, even incredibly rare decays will eventually happen. Enough time passes and everything happens. If protons decay, then all ordinary matter will eventually dissolve. The black dwarfs, composed of protons and neutrons and electrons, will slowly evaporate. The neutron stars will break down. The cold, dead planets, the asteroids, the comets, every rock and every grain of dust, all of it will eventually decay into radiation and lighter particles. The material substance of the universe will fade away. This process will take an almost incomprehensible time. We're talking about 10 to the 40th power years or more. To give you some sense of this time scale, consider that the current age of the universe is about 10 to the 10th power years. 10 to the 40th is 10 to the 30th times larger. That's a factor of 1,000,000 trillion. The time required for protons to decay is so much longer than the current age of the cosmos that the comparison is essentially meaningless. But in a universe with infinite future time, even incredibly slow processes eventually complete. After the protons decay, what remains? Mostly black holes. Black holes don't care about proton decay because they're not made of protons in any conventional sense. The matter that fell into a black hole has been compressed beyond recognition, transformed into something that has mass and spin and charge, but no other properties. Black holes will persist long after all ordinary matter has dissolved, but even black holes are not eternal. In 1974, Stephen Hawking made one of the most remarkable theoretical discoveries in the history of physics. He showed that black holes are not completely black. They emit radiation. This Hawking radiation arises from quantum effects near the event horizon, the boundary beyond which nothing can escape. Virtual particle pairs are constantly popping into existence throughout space, a consequence of quantum uncertainty. Normally, these pairs annihilate each other almost instantly. But near a black hole's event horizon, one particle can fall in while the other escapes. The escaping particle carries energy away from the black hole, causing it to slowly shrink and eventually evaporate. Hawking radiation is incredibly faint. For a black hole with the mass of our sun, the temperature of the radiation would be about 60 billionths of a degree above absolute zero, far colder than the current cosmic microwave background. Such a black hole would actually absorb more energy from the CMB than it emits through Hawking radiation, causing it to grow rather than shrink. Only when the universe has cooled below the temperature of a black hole's Hawking radiation will the black hole begin to evaporate. For stellar mass black holes, the evaporation time is about 10 to the 68th power years. For supermassive black holes like the ones at the centers of galaxies, the timescale is even longer. A black hole with 1 billion solar masses would take about 10 to the 100th power years to evaporate. That's a 1 followed by 100 zeros. This number is called a googol, and it's so large that it exceeds the number of atoms in the observable universe by an almost inconceivable factor. But eventually, given enough time, even the largest black holes will evaporate. They will shrink, their Hawking radiation growing hotter and more intense as they diminish, until in their final moments, they explode in a burst of particles and radiation. The last black holes will be the last complex structures in the universe, the final remnants of the cosmos's matter-dominated era. When they're gone, there will be nothing left but radiation, a thin soup of photons and elementary particles spreading through an ever-expanding void. This is the heat death of the universe, the ultimate cold, the final equilibrium toward which all physical processes tend. In this state, the temperature will be as close to absolute zero as physics allows, held above zero only by that irreducible quantum jitter, the 0-point energy that can never be removed. There will be no temperature gradients, no energy flows, no processes that can do useful work. The universe will be in perfect thermodynamic equilibrium, the most probable state, the state of maximum entropy. In the heat death, nothing can happen. Stars can't form because there's no mechanism for gas to collapse. There's no gas anyway, just radiation. Life can't exist because there's no energy to power metabolism. Even thought, even computation, becomes impossible because there's no energy gradient to drive information processing. The universe will be timeless in a sense, because time requires change, and change requires energy gradients, and energy gradients will have vanished. The cosmos will simply exist, cold and dark and silent, for eternity. How long will the heat death last? Forever. Or rather, The concept of duration begins to lose meaning. There will be no more events by which to mark the passage of time. The universe will have reached its final state, and that state will persist without change for timescales that make even the evaporation time of supermassive black holes seem brief. But here's the thing. The heat death is not something to mourn. It's not something to fear. It's not a failure or a punishment or a tragedy. It's simply the natural evolution of the cosmos, the inevitable endpoint of the processes that have been operating since the Big Bang. The universe is doing what all physical systems do when left to themselves. It's approaching equilibrium. It's maximizing entropy. It's spreading energy as evenly as possible. The heat death is not the universe failing. It's the universe succeeding in the only way physics knows how. And in the meantime, in the brief cosmic moment between the Big Bang and the heat death, remarkable things have happened. Stars have formed from primordial hydrogen, their cores reaching temperatures of millions of degrees, fusing light elements into heavier ones. Planets have coalesced from stellar debris, their surfaces cooling and stabilizing, their atmospheres creating the conditions for chemistry and complexity. Life has emerged on at least one of those planets, perhaps on many others. Evolution has produced intelligence. Consciousness has awakened. Beings have looked up at the night sky and wondered about their place in the cosmos. You are one of those beings. You exist in this narrow window of cosmic time, after the universe has cooled enough for complexity to exist, but before it has cooled so much that complexity becomes impossible. You live in the era of stars, the brief bright interlude between the cosmic dawn and the eternal night. This era has lasted about 14 billion years so far. It might last another 100 trillion years before the last stars die. But even 100 trillion years is nothing compared to the darkness that follows. The era of stars is a flash, a heartbeat, a momentary flicker of warmth in an endless cold. The Boötes Void, that 330 million light-year sphere of emptiness, is a preview of what all space will eventually become: cold and dark and empty. It's a glimpse of the universe's future, a window into the eternal night that awaits. Standing at the center of the Boötes Void would be the closest you could come to experiencing the heat death without actually traveling there in time. The darkness, the cold, the isolation, the absence of almost everything, that's what the entire universe will eventually be like. But the Boötes Void is also a reminder of how remarkable the non-void regions are. The fact that galaxies exist at all, that stars burn and planets form and life evolves, is extraordinary. It didn't have to be this way. The universe could have been uniformly empty from the start. If those primordial density fluctuations had been slightly different, if the initial conditions had been arranged another way, there might never have been structure at all. No cosmic web, no galaxies, no stars, no planets, no life. Just void everywhere from the beginning to the end of time. Instead, quantum fluctuations in the early cosmos created the seeds of structure. Tiny variations in density, imprinted during the first fraction of a second of existence, grew under the influence of gravity into the cosmic web we see today. Dense regions became galaxies. Galaxies clustered into groups and clusters. Under-dense regions became voids. And in the dense regions, in the filaments and walls and clusters, incredible things became possible. Stars formed and lived and died. Heavy elements were forged and scattered. Rocky planets coalesced from the debris. Oceans formed. Chemistry became biochemistry. Life emerged. Intelligence evolved. And here we are. The cold of the Boötes Void is the default state of the universe. The warmth of stars and galaxies is the exception, a temporary deviation from equilibrium, a brief rebellion against the second law of thermodynamics. We live in an exceptional place, at an exceptional time, experiencing an exceptional moment in cosmic history. The heat death will come eventually. The cold will claim everything. But for now, for this brief bright moment, the universe is alive with energy and complexity and wonder. There's a profound connection between understanding the coldest places in the universe and understanding our own existence. The physics that explains why the Boötes Void is so cold is the same physics that explains why stars shine, why planets form, why chemistry works, why life is possible. Temperature at its core is about energy and motion, and energy and motion are what make everything happen in the universe. Stars convert mass into energy through fusion. That energy radiates outward, warming planets. That warmth drives the chemistry that builds complex molecules. Those molecules, given billions of years, can organize themselves into living systems. And living systems can become conscious, can wonder about the universe, can ask why it's cold in some places and warm in others. The journey from the Big Bang to conscious beings asking questions about cosmic voids is a journey along the temperature gradient of the universe. We exist because the universe started hot and is becoming cold. We exist in that gradient, powered by the flow of energy from hot to cold. Stars are hot. Space is cold. Life exists in between, extracting energy from the flow. When the flow stops, when everything reaches the same cold temperature, when there are no more gradients to exploit, life as we understand it becomes impossible. We are creatures of the gradient, children of the cosmic cooling, temporary patterns in the long slide toward equilibrium. Understanding this doesn't diminish us. If anything, it makes us more remarkable. We are not just observers of the universe. We are part of its thermal history. We are the universe's way of experiencing itself during this brief, warm moment. The atoms in your body were forged in the cores of stars that lived and died billions of years ago. The energy that powers your thoughts ultimately came from nuclear fusion in the sun. You are made of star stuff, animated by starlight, thinking thoughts that are possible only because the universe hasn't yet reached its final cold equilibrium. What should we do with this knowledge? How should we feel about the cold that awaits? These are not questions physics can answer. They're questions of meaning and value, questions for philosophy and religion and individual conscience. But let me offer some thoughts. Perhaps we should feel gratitude. Gratitude for the unlikely circumstances that allow us to exist. Gratitude for the stars that warm our corner of the cosmos. Gratitude for the complexity that has emerged from simple beginnings. The universe doesn't owe us warmth. It doesn't owe us existence. The fact that we're here contemplating these questions is itself remarkable. Against the backdrop of eternal cold, our brief moment of warmth is a gift. Perhaps we should feel motivation. If the universe's warmth is finite, if the time for complexity and life is limited, then what we do matters. The choices we make, the knowledge we create, the connections we form, the love we share, all of it takes on significance against the backdrop of cosmic cold. We are the universe experiencing itself, understanding itself, celebrating itself. That opportunity won't last forever. We should use it well. Or perhaps we should simply feel awe, deep, profound awe at the scale of it all. Awe at the cold that stretches across 330 million light years of void. or at the heat that burns in the hearts of stars, or at the quantum jitter that prevents perfect stillness even at the lowest temperatures, or at the fact that anything exists at all when it would have been so much simpler for there to be nothing. The universe is not required to be comprehensible. The fact that we can understand it, even partially, is itself astonishing. The Boötes Void is the coldest place that exists, or close to it. 2.7 Kelvin, minus 270 degrees Celsius, just a few degrees above absolute zero, just a few degrees above the point where atomic motion nearly ceases. In that cold, atoms barely vibrate. Quantum effects hover at the edge of dominance. The normal rules of everyday physics strain towards something stranger and more fundamental. And in that cold, remarkably, 60 galaxies persist. Billions upon billions of stars continue to burn. Planets orbit those stars. Moons orbit those planets. And perhaps, just perhaps, life exists there too. Life that looks out at an almost empty sky and wonders if it's alone. Life that experiences the cold of the void as its normal environment, never knowing that denser regions exist where the sky is full of galaxies. They might believe they inhabit the only island of matter in an infinite ocean of nothing. They would have every reason to think so. And in a sense, they would be closer to the universal truth than we are. Because the void is the rule. The galaxies are the exception. The cold is eternal. The warmth is brief. The universe is vast and cold and mostly empty. A truth that becomes clearer the deeper we look into space. But it's also remarkable and complex and, in places, surprisingly warm. The Boötes Void reminds us of what the default state is. The galaxies and stars remind us of what's possible when conditions are right. And we, here on Earth, in our small corner of the cosmos, orbiting an ordinary star in an ordinary galaxy, have the extraordinary privilege of understanding both. We can grasp the cold, we can appreciate the warmth, we can see our place in the vast sweep of cosmic history, from the hot, dense beginning to the cold, dark end. Thank you for taking this journey with me into the coldest place that exists. We've traveled from the familiar cold of winter days to the extreme cold of absolute zero. From the emptiness of the Boötes Void to the physics of Bose-Einstein condensates. From the dying gasp of the Boomerang Nebula to the eternal silence of the heat death. We've seen how temperature connects to motion, how quantum mechanics prevents perfect stillness, how the structure of the universe arose from tiny fluctuations in the primordial plasma. If you found this exploration meaningful, a like or subscribe would really help the channel grow. It's a small gesture, but it means a lot. And the next time you look up at the night sky, remember what lies beyond the stars you can see. Beyond even the galaxies, beyond everything visible and known. There are vast regions of almost perfect cold. Regions where the temperature hovers just above absolute zero. Regions where the universe approaches its default state. The Boötes Void is out there, 330 million light years across, waiting in the darkness, a preview of eternity. And remember that you, warm and alive and conscious, are the exception. You are the cosmos defying the cold, at least for now. You are made of atoms forged in stellar cores, assembled by billions of years of cosmic evolution, animated by processes that will eventually cease. Your warmth is temporary. Your awareness is precious. Your existence is improbable and wonderful. Sleep well tonight, here on this warm world orbiting a warm star in a warm galaxy. The cold is out there, vast and patient and eternal, But it will wait for a long, long time, trillions upon trillions of years. And in the meantime, there is a light, there is warmth, there is life, there is love, there is wonder, there is you, listening to these words, thinking these thoughts, feeling whatever you're feeling right now. The cold will come eventually, but that time is not today, not tomorrow, not for eons beyond counting. For now, the stars are burning. For now, the universe is alive. For now, we exist. And that is enough. That is more than enough. That is everything. Good night.